Motor rotates by providing electricity. They spin using the basic concepts of magnet. Opposite poles, north and south, attract each other, and the like poles, north-north or south-south, repel each other. Each cycle, the motor applies these principles using two magnetic fields. One remains stationary, while the other rotates. The stationary part is called stator, and the other part called rotor or armature. Let's have a look on brushed DC motor structure and point out where are these two sources of magnetic field. First source of magnetic field results from the permanent magnet, represented by north and south pole, and that's the fixed source, the stator. And the second source of the magnetic field results from the wire carrying current. The magnetic field will be generated once the current is flowing onto the coil, and this coil is placed over the rotating part, which is the rotor. Then we have something called commutator. It's a split metal ring attached to the coil and placed over the rotor as well. And finally, we have brushes. These are carbon pieces that touch the commutator and supply electricity. Well, let's see how brushed DC motor spins then. When DC power is applied, current flows from the power source through the brushes, then into the commutator and finally into the coil. The rotor coil gets energized and creates a magnetic field in the coil, which interacts with the stator magnets, causing attraction and repulsion and making the rotor to rotate, so that its north and south pole align with the stator's south and north pole respectively. In short words, the interaction between the rotor's magnetic field and the stator's magnetic field causes the motor to spin. However, once both magnetic fields are aligned, the rotor would naturally stop. Now we need another push. We need any change in magnetic fields in order to make the rotor spin again. So to do that, we need to reverse the polarity of the coil, so that the magnetic field of the coil is generated in the opposite direction and keep interacting with the permanent magnets. But how do we reverse the polarity then? That's where the commutator comes in. As the commutator rotates, it reverses the polarity of the current in the coil, causing a change in the direction of its magnetic field. As a result, the coil rotates to align with its new orientation. This explains why brushed motors need brushes, to maintain electrical contact with the commutator in order to reverse the polarity of the magnetic field each time the motor rotates 180 degrees, resulting in smooth and continuous rotation. However, brushes wear out over time, leading to maintenance and efficiency loss, which is why brushless DC motors eliminate them completely. The same idea is being used in BLDC motors, the idea of having two sources of magnetic field. One is generated by the stator and the other by the rotor. The stator has multiple copper windings arranged in phases, and that's the first source. And the rotor has the permanent magnet attached to it, usually 4, 6 or 8 poles. But this example is just for simplification. Let's see how BLDC motors spin. Instead of brushes and a commutator, a BLDC motor relies on electronic switching of the current through different windings. The current is first applied to the stator coils. This creates a magnetic field around that coil. The coil acts like an electromagnet with a north and south pole. The north pole of the coil attracts the south pole of the rotor magnet, and the south pole of the coil repels the south pole of the rotor magnet. After the rotor has been aligned with the stator magnetic field, the motor will stop. Now we need another push to keep the motor spinning. Here then comes the electronic switching. The controller changes the current path to the next coil in the stator, and the new coil is energized and the magnetic field shifts, pulling the rotor further. This process repeats in a precise sequence, creating continuous rotation. You see here how the controller is switching the current between the three phases, A, B, and C. To keep the motor spinning, the current is applied between phase A and C, so that phase A acts at the north pole and attracts the south of the rotor. The phase C acts at the south pole and repels the south of the rotor. Then the next step, the controller will switch the current to flow in phase B and C, causing the attraction and repulsion. And then phase A and B. Then A and C again, but this time phase A acts at the south pole and phase C acts at the north pole. And the same concept goes with the other steps, but the polarity is reversed at the same phases. Let's have a look on quick comparison between the two motors. BLDC motors offer several key advantages over traditional brushed motors. One of the biggest benefits is the absence of brushes, which significantly reduce wear and tear, leading to a longer lifespan and lower maintenance. Additionally, BLDC motors are highly efficient because they eliminate friction losses caused by brushes, allowing more electrical energy to be converted into mechanical power. Another major advantage is the precise control, as the speed and torque of the BLDC motor can be regulated electronically, making it ideal for applications requiring accuracy. accuracy. Finally, BLDC motors provide more power for their size, thanks to their high torque to weight ratio, making them perfect for compact and high performance applications. If you found this video helpful, make sure to like and subscribe. Thanks for watching and see you in the next video.